So based on the bipolar bit representation, we are now going to introduce the log likelihood ratios, which are the very important concept for representing the messages that we pass in message passing decoders. So we start right ahead with the definition, and the definition actually is not so difficult, and we can jump right in. So we start with a random variable x, and x is a binary or bipolar random variable. So this is important. So it doesn't work for any random variable, it just works for the specific class of binary random variables. For binary random variables, we can define the log likelihood ratio as follows. So the log likelihood ratio L of x is the logarithm, and we use the natural logarithm, so the logarithm to the base e, of the probability that x is equal to 0 divided by the probability that x is equal to 1. And equivalently, for the bipolar bit representation, this is the same as the natural logarithm of the probability that x double dot is equal to +1 divided by the probability that x double dot is equal to -1. That's the log likelihood ratio. We can also define a channel transition log likelihood ratio. And this is defined as L of y given x. That's the logarithm of f of y given x equals 0 divided by f of y given x equals 1. So P is the PDF. So P is something that we could denote as f of y given x of y given x. So we have the channel transition log likelihood ratio, P of y given x, or f of y given x, divided by f of y given x equals 1. So we have the condition x equals 0 in the numerator, the condition x equals 1 in the denominator. And similarly, we can condition this also on the bipolar representation. So this is P of y given x double dot being equal to +1 divided by P of y given x double dot being equal to -1. So these are the definitions of the channel transition log likelihood ratios. And the log likelihood ratios, they have some important properties. So why should we use them? Mainly because they have a lot of advantages when it comes down to hardware implementation. So when we work with probabilities, probabilities are a very nice concept to work with when we have pen and paper, but not in a computer. Because we are very often dealing with very small probabilities or very high probabilities. And then we need a lot of bits to represent these probabilities sufficiently fine to capture all the dynamics that happen inside a device or a decoder. And these dynamics, they can be avoided by the use of the logarithm. The logarithm essentially compresses the probabilities to a smaller dynamic range. So we have less numerical instability issues because of this logarithmic representation. Then also, when we work with probabilities, we always need to take care that the probabilities are properly normalized. We need to ensure that P of x equals 0 plus P of x equals 1 is equal to 1. And if this is not the case, so for instance, if we have a P tilde of x equals 0 plus P tilde of x equals 1 is not equal to 1, then we need to normalize. So then what we do is we have P tilde of x equals 0. So note that P tilde is not a probability, but it's something that is not normalized, divided by P tilde x equals 0 plus P tilde x equals 1, plus P tilde of x equals 1, divided by P tilde x equals 0 plus P tilde x equals 1. This will be equal to 1 because we normalize. This is the normalization factor C, See, this is the same normalization factor. And now when we calculate the log likelihood ratio, essentially what we do is we divide this term by this term, and this normalization factor will cancel. So we don't need the normalization factor, because when we calculate natural log of 1 over c times p tilde x equals 0 divided by 1 over c, p tilde x equals 1. This normalization factor 1 over c will just cancel, and we don't need to compute. So we avoid a normalization step, which is also a big deal because this normalization step can be very nasty. So this is another advantage that is very important. We cancel normalization factors. We don't need normalization factors. Then the next advantage that we have is that log likelihood ratios can be very easily computed, as we're going to see, at least for the commonly used channels. Second advantage is that we often need to multiply probabilities. And we know from digital electronics that multiplications are bad. Multiplications are very costly. In order to realize a multiplier, you need to have multiple full adders in a sequence, and the critical path is complicated, or you need to have flip-flops in between, so which complicates or increases the hardware costs. Now, because of the logarithm, you essentially transform a multiplication into an addition. And we know additions are nice. So what we will have is that multiplications become additions. So that's another advantage. Because of these advantages, most decoders that we see today in practice, they use log likelihood ratios. I would even go as far as say 99.99% of implemented decoders, they use log likelihood ratios. So let's take a look at the binary symmetric channel and some properties for the binary symmetric channel. So we know that we have two inputs, either x or x double dot, so x double dot plus 1, x double dot minus 1, and we make an error with probability delta. So we can define the channel transition probabilities p of y given x. It's either 1 minus delta or delta. So now we can calculate the log likelihood ratio, and we can calculate the log likelihood ratio first for the case y is equal to 0. If we recall, if we just go back 2 slides, we saw that this was for one very specific y. We don't change the y over here, so this is fixed. This is not a random variable. What we change is the x. This is for one very specific realization of y. So we calculated the log likelihood ratio for y equals 0, and we just insert the values. So insert p of y equals 0 given x equals 0 divided by p of y equals 0 given x equals 1. 1 minus delta over delta. So this is the natural log of 1 minus delta divided by delta. Okay, so next we're going to do the same calculation for y equals 1. We do it for y equals 1. We calculate p of y given x equals 0 divided by p of y given x equals 1. This is the log of delta divided by 1 minus delta. And we can write this as minus the log of 1 minus delta divided by delta. Just because we take this to the power minus 1, and then we take the minus sign in front of the logarithm. So to summarize, we can say that L of y given x is equal to either ln of 1 minus delta over delta if y is equal to 0, or minus ln of 1 minus delta divided by delta if y is equal to 1. We can take the two cases, we can generalize the two cases as minus 1 to the power y times log 1 minus delta over delta, or y double dot times this constant. Log of 1 minus delta divided by delta is a constant, and we call it LC, the channel reliability parameter, LC. So the log likelihood calculation is essentially just the channel output on bipolar representation multiplied by a channel reliability parameter, which is ln of 1 minus delta over delta. We can see if delta is small, this value will become very large. So it's essentially 1 divided by 0, which is infinity. So it's tending towards infinity. And if delta is 0.5, which is the worst possible channel, then this is equal to 0. So this is 0.5 divided by 0.5, log of 1 is equal to 0. So LC defines how good or bad the channel is. So the channel reliability parameter. Okay. So let's take a look at the binary input AWGN channel. So again, we can now formulate the conditional PDFs, P of y given x double dot. So this is the Gaussian distribution. So it's 1 over the square root of 2 pi sigma n times e to the power minus y minus 1 over 2 sigma n, or y plus 1 squared over 2 sigma n, depending if we transmit a plus 1 or a minus 1. And then we again just insert. So again, this holds for a specific y. And then we insert in the numerator, we take x double dot equal to plus 1, 0. And in the denominator, we take x double dot being equal to minus 1. And this is now the natural log of this term. So we just insert. And again, we see first that these normalization factors are, because we need the integral over the PDF to be equal to 1, the normalization factors cancel. And then we have log of exp. This is nice because log of exp just cancels each other. And then we have, recall that if you don't remember, ln of a divided by b is equal to ln of a minus ln of b. So we have log of x cancels. So we have this term minus log x cancels this term. So it's minus y plus 1 squared over 2 sigma n squared plus y plus 1 squared over 2 sigma n squared. Now we're just applying our quadratic equation, and then we can simplify these terms. So it's 1 over 2 sigma n squared minus y squared plus 2y minus 1 plus y squared plus 2y plus 1. A couple of stuff cancels. Minus y squared plus y squared cancels. And minus 1 plus 1 cancels. So we are left with 2y plus 2y, 4y divided by 2 sigma n squared. So let's summarize. We have L of y given x equals 2 over sigma n squared times y. So again, it's y multiplied with the channel reliability parameter. Very nice. So we just take our channel output and we multiply it with a constant, then we have the log likelihood ratios. Again, this constant is 2 over sigma n squared, or equal to 4 times ES over N0. So this is channel reliability. If signal to noise ratio ES over N0 is large, the channel reliability parameter is large. If ES over N0 is small, then we have bad channel, the channel reliability parameter is small. So very nice result, because it means in the case of the binary input AWGN channel, we obtain the log likelihood ratios by multiplying the received value with a constant LC that just depends on the channel parameter. So again, this makes log likelihood ratios very attractive for real systems because we just take the channel output, multiply with a constant. We avoid all logarithms, exponentials that we would need to compute when we were to evaluate the probability P of y given x. Everything is avoided, and we have this very nice expression, and we have all the advantages of log likelihood ratios. So it seems like a very perfect match. So some properties of the log likelihood ratios. First property, or first we look at what happens for different corner cases. So first corner case, we assume that the x is uniformly distributed, so P of x equals 0 is 1/2. Then we have the log of 1/2 divided by 1/2. This is log of 1. This is equal to 0. But then we have a log likelihood ratio of 0 if the two, if x equals 0 is the same as probability of x equals 1. Now let's assume that x equals 0 is probability that x equals 0 is larger than the probability that x equals 1. So then we calculate L of x, and because the numerator is larger than the denominator, this guy will be larger than 1, and it means that the logarithm of something larger than 1 will be positive. So this will be positive. We have equality 0 if both probabilities are the same. If x equals 0 is more probable than x equals 1, we have a positive log likelihood ratio. And if the probability that x equals 0 is smaller than the probability that x equals 1, we see that we get a negative log likelihood ratio. So the sign of the log likelihood ratio tells us something about which outcome of the binary random variable is more likely. That's also a very nice property of the log likelihood ratios, because we can divide them into the sign and the magnitude. So the sign of the log likelihood ratio indicates the most probable binary value. So if we maximize over which one is more probable, either 0 or 1, we can just take the sign of the log likelihood ratio. This is very important in the decoder, because if you have a log likelihood ratio that is positive, we can say that the bit corresponding to this log likelihood ratio was most likely equal to 0. We can decide this bit to be equal to 0. The log likelihood ratio is negative, means that we can assume that the bit was most likely a 1. And the magnitude of the log likelihood ratio indicates how reliable the decision is. If the magnitude is very small, the two probabilities are more or less equal. They are more or less the same. If the magnitude is very large, it means that one of the probabilities is significantly larger than the other one. And we see this for the binary symmetric channel, because there the magnitude corresponds to the channel reliability parameter, and also for the binary input AWGen channel, of course. And that's that's telling us how reliable the decision is. So now let's take a look at the inverse relation. So assume that we have given a log likelihood ratio and we would like to calculate a probability. So what we do for doing this calculation is the following. So we start with a log likelihood ratio x, L of x, and we write L of x. And now we know that, because we have a binary random variable, we know that P of x equals 0 plus P of x equals 1 is equal to 1. So we can say that P of x equals 1 is equal to 1 minus P of x equals 0. That's what we do here. So we replace P of x equals 1 with 1 minus P of x equals 0. And now we have an equation that just depends on P of x equals 0, so we can rearrange and solve. First, we take everything to the exponent to get rid of the log. And then we solve this expression for p of x equals 0 just by rearranging a little bit. So it's very good if you try to follow this step for yourself. And we'll find that p of x equals 0 is e to the power L of x divided by 1 plus e to the power L of x. If we don't like too many e's, we can also multiply this in the numerator by e to the power minus L of x and in the denominator by e to the power minus L of x. And we get 1 divided by 1 plus e to the power minus L of x. Because this multiplied by this is e to the power minus L of x here, and this multiplied by this is equal to 1. We can say that this is 1 divided by 1 plus e to the power minus L of x. Okay, so we have p of x equals 0. How do we get p of x equals 1? Just take 1 minus this expression. So p of x equals 1 is 1 minus this expression. When we bring this to common denominator, simplify, we get 1 to the power 1 plus e to the power L of x. So we can simplify this. So p of x equals 0 is 1 divided by 1 plus e to the power minus L of x. And p of x equals 1 is 1 divided by 1 plus e to the power plus L of x. Again, we can bring the two expressions together and bring them together with the bipolar representation is the following. So the probability that x double dot is equal to x double dot is 1 divided by 1 plus e to the power minus x double dot times L of x double dot. Or you don't like the double dots, so the probability of x, so x is binary, is 1 divided by 1 plus e to the power minus 1 to the power x times L of x. Okay, so very, very nice. So we have this representation, this unified representation that we see here or here for transforming log likelihood ratios and probabilities. Now we can transform them back and forth. So what we do now is, and this may not immediately obvious why we need it, but as you can see here, we store this. This will become obvious later. So this will be an expression that is going to be useful later. So we calculate the expectation of x double dot. So the expectation of x double dot is plus 1 times the probability that x double dot is equal to plus 1 plus minus 1 times the probability that x double dot is equal to minus 1. So this is the probability that x double dot is equal to plus 1 minus the probability that x double dot is equal to minus 1. Or to keep things binary, this is the probability that x equals 0 minus the probability that x equals 1. Because the probability that x equals 0 is 1 minus the probability that x equals 1, this is 1 minus 2 times the probability that x equals 1. That's the expected value of x double dot. So, the probability that x equals 1 is 1/2. The expected value is equal to 0. Because then x double dot is plus 1 minus 1 with same probability, and on average you have a 0. So now can we rewrite this expression in terms of log likelihoods? So that's what we do next. So we insert the definition of the log likelihood ratio or the calculation of the probability from a log likelihood ratio. So we know that p of x equals 1 is 1 over 1 plus e to the power L of x. We multiply by 2, so that's 2 in the numerator, and we have this expression. And when we further bring this on a common denominator, we get 1 plus e power lx minus 2 over 1 plus e power lx. And rewriting this is e to the power lx minus 1 divided by e to the power lx plus 1. Now this looks like something that may be studied because it seems like something very general or very regular. And indeed, this is a very common function. This is the hyperbolic tangent, or something very close to the hyperbolic tangent, because the hyperbolic tangent of some input tau is defined as e to the power 2 tau minus 1 divided by e to the power 2 tau plus 1. So we can say that this is the hyperbolic tangent of L divided by 2. So the expected value of x is 1 minus the power 2 times the probability that x is 1, 1 minus 2 times probability that x double dot is equal to minus 1 is the hyperbolic tangent of Lx divided by 2. And this is something that we're going to need later on. Okay. So now in decoding, we very often have a posteriori log likelihood ratios, and we can define a posteriori log likelihood ratios as follows. Essentially, we define them in the very same way as we defined the previous log likelihood ratio, but now we move the binary random variables in front, and we have given an observation y. So we have a binary channel input x given a channel output y, and this is again the log of p of x equals 0 given y divided by the log of divided by p of x equals 1 given y. So essentially, it's just the same expression applied a posteriori log likelihood ratios. So we can massage this expression a little bit. So L of x equals y is we insert the definition. So we insert the a posteriori probabilities p of x equals 0 given y divided by p of x equals 1 given y. And then we apply our very good old friend Bayes' theorem. And we get p of y equals 0 times p of x equals 0 divided by p of y. This p of y is a nasty normalization term, which will cancel out because we need to divide numerator and denominator by p of y. So both of them will cancel. So then we divide by p of y given x equals 1 and divided by p of x equals 1. And now again, we can split these two terms because of the log rules. So the logarithm of multiplication becomes the addition of logarithms. So this is ln of p of y given x equals 0 divided by p of y x equals 1 plus ln of p of x equals 0 divided by p of x equals 1. So this is the log of y given x plus the log likelihood ratio of x. And if both x equals 0 and x equals 1 are equally probable, this term is equal to 0, and we know the a posteriori equals the a priori, except that there is this normalization term, and this normalization term cancels in log likelihood ratios. So in this case, the log likelihood ratios are the same. So they are equivalent. So that's also a very nice property because this normalization term will cancel out. Okay, so this is the introduction to log likelihood ratios, and next we're going to see how log likelihood ratios can be applied in the context of LDPC codes.